Very happy to say that we have Cristobal Petrovich to give our formal seminar. Cristobal, we're welcoming him back because Cristobal was a PhD student here from 2010 to 2015 over at the university, but actually spent a lot of time at the Institute because he was advised by Scott. Cristobal then went on to CETA, where he was a postdoctoral Prize Fellow, and then to Arizona, where he was a Bock Fellow, before joining the faculty at Universidad Católica as an assistant professor, and then a couple of years ago moved to Indiana University at Bloomington, which is where he is now. Cristobal is an expert on things that are dear to many of the hearts of many people in this room. So exoplanetary dynamics, the architectures of exoplanetary systems, as well as compact object mergers, LIGO, Virgo gravitational wave sources, and so on. And today he's going to tell us about how cold Neptunes shape planetary systems.
Okay, thank you, Chris. Thank you for the introduction, and thank you for coming on this rainy day. Initial title was how cold Neptunes shape planetary orbits, but I decided to include more stuff on resonances and in particular on hydrodynamic simulation that we have carried out also in my group. So the new title reads now From Resonant Chains to Chaos. The idea will be to see if there is a broad theme in the planet formation process where planets are initially assembled in resonances, and if they do, whether they remain like that or they just get disrupted. And we show there seems to be an emerging picture pointing towards the broken resonant chains. And this is work that I will highlight from students at Indiana University. Two PhD students, Juan Ignacio, who is here, was a PhD student at Católica, and a postdoc at IU with me at Católica. Just to have everyone on the same page, previous to 1995, these are the planets that we knew around main sequence stars. This is the semi-mirror axis and planet mass. The first planet discovered was 51 Pegasi D of Jupiter, that triggered the first exoplanet puzzles of how these Jupiters form and whether they, for instance, migrate. The velocity service continue finding planets, and in particular with the baselines extending all the way up to 10 or 20 years, it was found that actually these hot Jupiters tend to be rare, in about 1% of sun-like stars. And the most common way of these planets form is in wide orbit separations, what we call 10 hot Jupiters. With the transit service, we start finding planets in a different parameter space. The most common population, mostly from Kepler, is this population of super-Earths, of sub-Neptunes. And this region here is fairly limited because of selection biases against small planets of wide separations, and also by the baseline. But in a nutshell, with these two detection techniques, we can infer that planets seem to be preferring orbits that are actually fairly close to the host star. There's a lot of material in the inner, say, 0.1, 0.2 astronomical units. If you take, for instance, many people have actually worked on this. If you take the statistics from Kepler, we roughly have to think that there are in the order of 3 planets with a wide distribution inside the orbit of Mercury, with each of the planets, the super-Earths of sub-Neptunes with masses of about 5 Earth masses. So it's about a Neptune mass already in regions that are about like 0.1 astronomical units. Right? So the question of migration, how do you get these solids, is not only triggered by the hot Jupiters, but also by the super-Earth. Other techniques start populating different regions. This is from microlensing, which is highly insensitive to the planet masses. And you start getting all the detections, mostly at few astronomical units, which are the typical sizes of the Einstein rings. I will come back to this at the end of the talk. And there are image planets in wide orbits, normally self-luminous. So the main goal, and one of the main goals in the field, is to use this plot, the demographics of exoplanets, to infer how these planets form. And one of the big problems in the field is the question of planet migration. is a fundamental problem in our theories of planet formation and evolution. If you implant a planet in a gaseous disk, it lands to these spiral density waves that carry energy and angular momentum. As a back reaction, the planet actually can migrate. And in the simplest model from the early theories from the 80s, it was predicted that planets should actually migrate very fast. So the problem here being that if planets do migrate extremely fast, they should either accumulate at this inner edge or just fall into the star. Unless we modify the migration, for instance, to detailed thermodynamics of the disk that people have involved to reverse the migration, or effects from multi-planet systems captured into resonance. But something else, like the theory itself does predict that the planets migrate very, very big. That fails to reproduce the data.
Well, this is unless they open that gap and, switch to type 2 migration, which is much slower.
Yes. Yeah, so for the Kepler planets, they barely open gaps and they would migrate very quickly. So the cores themselves would migrate fast.
Well, for Neptunes, that may not be true. They may open.
Right, so in the internet, right, so the thermal masses are relatively small, smaller than that, are comparable to 5 Earth masses for typical parameters. I agree. So just to illustrate how different models could track differently in this plot of semi-mirrored axis and planet mass, this is the canonical way that we think that planets like hot Jupiters form. We have the assembly of rocky cores at the wide separations from the co-star. The core reaches a critical mass that undergoes runaway accretion, and then it can follow migration. And these are some tracks from the Bayer model. So this is one possibility. Another possibility is that because we know that Kepler planets are actually, already you have about a Neptune mass in these regions, you may be able to even assemble early on a core, and this is being proposed by colleagues and the entire. You can get in situ formation of these planets. So these are two drastically different scenarios, and people have tackled the question of migration using composition studies, for instance, atmospheric retrievals, forward modeling, like the Bayer model that I just showed, plots. And one of the things that I will focus on here, and the way to tackle this, is orbital architectures. Luckily, you don't only have one planet to start with. Normally, protoplanetary disks form a range of planets. So all these planets would potentially undergo migration. And if they do, we know that convergent migration can actually lead to the capture into orbital resonances. And this is from a review from Paolo Benitez-Jambay. This is showing a hydrodynamic simulation with 3 planets. All the planets are migrating in, and they get captured in this long chain of 1 to 2 to 4. And also that leads to a critical angle, a resonant angle to library, which is a combination of the mid-longitudes. Right, so this is a prediction from planet migration. So we observe these resonances in some of the systems. Possibly one of the most striking ones is HR 8799. It has 4 directly imaged planets. With astrometry, it's been argued that the 4 planets follow a long chain of 1 to 2 to 4 to 8. There's been a reason. This is the first exoplanet that was discovered by direct imaging embedded in a protoplanetary disk, PDS-70. And with the astrometric measurements, there's a potential chain also of 3 planets. But it's still debated. If we look into not the wide orbit giant planets, but short period planets, and we just pick the ones that are high multiplicity, meaning 6 or more planets. This is the sample that you get, mostly from Kepler and TESS. And those are going to be the ones that these very tightly packed systems that really represent the most pristine state of these planets. Maybe we're looking at the planets at the time when they left the protoplanetary disk. Out of these 7 systems, 5 are in resonant chains. A classic example is TRAPPIST-1. K2-138 has a sequence of 3 to 2 resonances, so extremely well tuned. And there is a bunch of other resonances, with the most common being 3 to 2. There is an exception on Kepler-11 and Kepler-90, but Kepler-90 also has a gas giant planet that maybe can actually disturb the resonances. So a big number of these very pristine systems has these resonant chains.
None of these are young host stars though, right? These are all.
This one is, one of these 2 eyes is relatively young. They will come back to that. Young meaning ages below, say, 100 million years. No, sorry. No, one of those is like 700 million years. This is, yeah.
Youngish.
Yeah. But we'll talk about the ones that are actually very young. Yeah. But the large majority are not like these planets that I showed you. The large majority are not in resonance. Instead, we think that dynamical instabilities have been shaping the orbits of these planets. And the emerging picture here is that planets seems to be forming with a high multiplicity, at least for the Kepler planets, in very dynamically cold orbits. They are then going instability, driving planetary ejections and planetary collisions. You start losing planets, the orbits become wider space, dynamically hot. This is pointing to like higher inclinations, higher eccentricities, and this process keeps going until you observe at the present time with lower multiplicity planets. And this picture mostly comes from coming back to this plot from transits and radial velocities. But in order to make that connection, I wanted to define first this line over here and overplot the saffron parameter of unity, where this parameter, depending on the stability, will tell you whether planets are likely to collide with each other or eject each other. Right, so it's a competition between the gravity from the planet and the gravitational potential from the star. So planets with high escape velocities are able to eject very easily other planets. In particular, Jupiter can eject things. And you're going to have collisions on this side of the planet. So the radial velocities in the regime where the saffron of numbering is much larger than unity, you mostly have ejections. So you expect to eject Jupiters and leave the planets. When you run the simulation, the scattering experiments, the orbits become eccentric, and that actually reproduces reasonably well the eccentricity distribution for the cold Jupiter planets, roughly following a Rayleigh distribution.
How many, what's the fraction that fall into the star? Can you remind me?
From the scattering?
Yeah.
I will show some of the results on that, but order of like 10%.
Okay.
Yeah. For the planets that are below unity, the ones leading to mostly planetary collisions, we think so. We have a degeneracy between inclinations and the intrinsic multiplicity. So it's very hard to tell what is the range of inclinations and what is the range of just based on transits themselves and just counting how many planets are transiting at a given time. But people have attempted, and we did that also with colleagues at CETA, then for the Kepler sample, breaking the degeneracy with transit timing variations. Other colleagues did it with transit durations or some sort of a forward model implied stability, and they all agree that the RMS eccentricities and inclinations tend to fall with the intrinsic number of planets. So following this picture, everything becomes dynamically cold, starts dynamically cold, you get collisions, and you start losing planets, but also becoming dynamically hotter following this strategy.
Cristobal, we're trying to understand why there are breaks in this curve.
Why there are breaks in this line?
Oh yeah, no, those are just due to the mass-radial relationship that I'm assuming.
Planetary, right?
Yeah, this is from Temaki. Yeah. So it's a schematic, but I was taking like the mass-radial relationship from Temaki spot. So one is for Jupiters, the other one is for Neptunes, and the other is for rocky planets. But regardless of the line, these two samples are well within
So
both
this is
extremes.
solar system specific. Is this with, placement of the planets?
No.
Equation of states.
No, this equation of state is actually empirical based on the
Okay,
observed exoplanet sample.
because you have the mass on that, okay, on this
Yeah.
basis, okay.
Yeah, this one is just Jupiter's, but this one needs to be fitted, especially for like subnatives. This is just rocky planets. Right. So to summarize, the models of planets migrating predict resonances should be common. But most exoplanets seem to be shaped by instability, erasing this primordial resonance structure. So the question then stands, were resonance prevalent early on and then disrupted, or they were actually not common at all at the beginning? So I will focus on two different things. So in part one, I will talk about the assembly of resonances, mostly with hydrodynamic simulations and comparisons to the images from ALMA. And in the second part, I will discuss the scenario where resonances are prevalent, how they're actually disrupted. Okay, so you have all seen these images from 2015. ALMA, this is H. Tau showing these very nice structures of dusty rings and gaps. Since the early results in 2015, people started invoking the idea that there are planets in the gaps, carving these gaps and rings. And there are a few caveats on this, and I'm happy to discuss this later too, but possibly a single planet can actually open multiple gaps. There could be another effects that produce these rings on the dust. So one of the things that we started thinking about is whether you can actually predict something else on the theory of this planic interaction that could be potentially observed.
How many of these observed things with gaps seem to have a planet in them?
So there are two systems with early image planets. One is PDS-70. There was a recent paper this year with a second early image planet inside a gap. It was in a scattered light, so it's another size distribution of that. And then there is more sort of indirect evidence from perturbed disturbances of the Keplerian flow, what people call velocity kinks on the and I don't have a statistic to that, and I think the numbers are contentious. So far, too. Well, I would argue that actually the system that I will show you does have planets. But we have to find something else to convince ourselves that is a planet which is carving the gap. We can start with PDS-70. There was a paper in 2023 showing that it's hard to see, but you have to believe that there is some dust here, cloud. It's actually separated by roughly 60 degrees. This is going in this direction. So it was suggested to be dusty material located at the L5 trailing Lagrange point. But that's the case where we have the planets. There are other cases like LKCA15, where we don't have any other evidence of the planet, but you see that the planet, there's a gap here. And if you just take the residuals, you see popping up actually with very high significance material in the Lagrange L and L4 of a potential planet that we haven't really detected. So one of the things that we've been trying to tackle here is whether we can actually use this as a way of tracing the presence of planets. And we do that, and by the way, there's another example, and all seem to be at L5, not L4. So one of the things that I've been doing with Agustin, a student in Indiana, is to try and understand whether this is a robust prediction from this planet interaction. So what I'm showing is just the gas after 1,000 orbits of a planet embedded here is at the origin, at the center, sorry. The only thing that we're varying from panel to panel is the temperature gradient that follows a power law beta. And what we're finding, sorry?
What's the viscosity? Is there viscosity?
Yeah, the alpha viscosity is like 10⁻⁴. Relatively low viscosity. Yeah. Right, so what you see is that the only thing actually, so first of all, it is robust. You get long-lived material in the Lagrange points. This is in the gas, but the dust will mostly follow. And we have also studied the dust. And the one thing actually regulating this is just the surface, the temperature profile of the disk. If the temperature is decaying with radius, we expect that you mostly get material accumulated in the Lagrange L5 point.
Residuals were with respect to a uniform disk model, so it's an overdensity
Yes.
at L4. Exactly.
Yeah, you take an average of rings, and you subtract it out. Yes,
This is density of gas?
this is the density of gas. We have that with dust too. We're working on that actually. But in principle, this picture would apply for dust that is well coupled to the gas. You will see the same. And it actually becomes very pronounced with dust.
What if you use the realistic beta of 8.3 or so?
Oh, this is just a schematic to show that you break the symmetry
Mhm.
with beta. You still get it.
Still get it.
Yeah.
Well, how are you breaking the symmetry?
Oh, it turns out that the temperature profile actually sets a different background in the disk. At least to sort of enhance more of the flow in one of the Lagrange points than the other.
It's not clear to me how.
No, it's happy to chat about that. Yeah, it gets a little detailed.
Okay.
But it's actually very subtle. We struggle with this problem quite a bit.
It's a 2D simulations, right?
These are 2D simulations. So we're including now dust and dust feedback. And, yeah. But people have seen it in 3D simulations too, this asymmetry. So people normally run the simulations and they include some more realistic power law for the temperature and still get normally. And they didn't understand in the simulations why they were getting material in the L5 point as opposed to, I don't know, something symmetric.
So you mentioned this a couple of times. What is this realistic power law and how do we know?
No, it could be a model of the disk. Passive heating.
What is this? What is the realistic number for that beta?
Around 0.3
Plus 0.3.
minus.
Minus.
Yeah, it is decaying. So for instance, because we know the rotation of this disk that I show, it has mostly material in L5 as opposed to L4. Which would imply in this context that actually the temperature gradient is actually negative, which makes sense. There is another system that has a crescent, similar that it was suggested to be material on one of the Lagrange points of a planet. Again, none of the planets are detected here, with the exception of one kink, one of the planets here. But if you zoom in, you see this crescent inside the gap. And if you believe that this pranic interaction create these structures, you might actually invoke the presence of a planet here such that the material is in the Lagrange L5 point. It's not actually on center. So something that we have done to model this disk is to include actually two planets that can do both. That can actually carve the gap. And one of the planets will create this crescent dusty structure. So long story short, this is the image from ALMA. This is the synthetic observation that we obtained from our model. This is a global model including the presence of many planets, actually two Saturns here. Oops. so two Saturns, and the tension should be actually placed on the crescent. Looks very similar.
A little bit of over density in the L4 point in the observation, in the synthetic observation as well, I guess. We look at the.
Oh, you mean here?
Yeah,
Could be, yeah. This is, yeah, it is possible, yes, you still get some.
There are many planetesimals.
Yeah, I'm gonna come back to the global model that we have, because we need several planets to actually carve all the gaps and rings.
How rigid are these problems? I mean, if I have enough planets on enough orbits, can I just get whatever I want? Or there's.
Presumably, yes. But you run into issues of stability. And here we're not only using the dust emission. This is one of the best studied protoplanetary days. We also compare it to the gas that it was observed in the CO. On our model, which has two signs, actually reproduce the data fairly well compared to just a Jupiter. And you can do even better than that and use the dynamics. So the orbits of these planets actually do follow a resonant chain. They're in 1 to 2 to 4. So, and you're gonna do even better. Because you have a model, you have the surface density of the disk, you can ask the question of whether these planets would actually capture into the resonance. So we can implement some damping of semi-mirror axis and eccentricities, run this in rebound, and ask whether they actually get captured or not. And we're using actually the aspect ratio that is derived from these thermodynamic models of the disk. And indeed, the planets get captured, this convergent migration, they get log, the inner set of Saturns is getting to the 43 resonance, and the eccentricity remains small. But you can do even better than that. Because if the planets are indeed actually in this resonance, you have a relation between the three variables, the mean longitudes. For low eccentricities, the longitudes are very similar to just the position angles. So you can convert the longitudes to relation between the position angles. So you can predict where the planet should be in the disk. Yeah, we have a planet 2 here. There was a claim of a planet 3 here through velocity kinks. So we take that and we can predict where the position of planet 1 should be, following the relation between the position angles. And soon after we submitted this to AAS and we didn't submit it to archive, we predicted there was a paper, there were actually two papers. There was a paper by Alarcon 2022 showing possible evidence of the position of a planet exactly here in where the cross is. This is just using atomic carbon emission. And this year there was J.W. Steiner paper also claiming that there is a planet, potentially a planet there. So maybe this is actually the first system that without having planets being observed, you can argue that the system is actually in a resonant state. And you're observing migration at the present time. The planets are still in the migration time. Okay, so how are resonances assembled? Early on, I show that HD 163296 is a possible example of migration using clamps around the Lagrange points. And we can use that prediction from this planet interaction to infer the presence of planets too.
If you have suppose that you start with a bigger sample, disks with some planets, and you migrate, how likely is it that they're going to get captured versus, let's say, dive into the star again, if they're low enough mass that they don't open a gap? In other words, is it a very plausible outcome, a somewhat plausible outcome, or a very rare outcome?
Yeah, so to answer that, this is not the best sample. These are very big planets. No, but also like very wide orbit planets. So
Okay,
this is one of the most massive protoplanetary these days.
right, I was more on the.
On the other
those
side, yes.
Compact systems that you showed in the beginning, yeah.
Yeah, which is part of the second,
Okay.
if resonances are prevalent, how they are disrupted, and I wanted to show a plot that there might be evidence that there are planets, starting resonance early on. So how do you break the resonances? One possibility is to have stellar flybys, for instance, and that's something that, we started with, Carolina Charlambos. They need to, and this is only relevant for, planets that are directly emit, like very wide orbit planets, like HR 8799. They need to come as close as 3 times the stellar-centric distance of the outer most orbit, roughly for 2 to 1. For 3 to 2, it could be they're very weak resonances and they can actually get disrupted more easily.
How frequent are those flybys?
Right, so these distances, and this is mostly thinking about like open cluster. This is part of a chemical moving group. You probably get order of magnitude about like 1 weight in 100 AU, give or take, in the lifetime of the open cluster, because then it becomes actually very, very rare.
So it's not surprising that HR 8799 survived.
So the fact that it's actually in this long tail of 2 to 1 resonances makes it actually more resilient. Yeah. If it was at the 3 to 2, it would be easily disrupted. It's actually very close to the verge of instability there. But it's somewhat protective actually. The other option to break the resonances is to just simply remove the disk. If we were to remove the disk in the model that I presented, it has a 4 to 3 resonance, it just breaks. If you're really thinking about short period planets, there's been a model called the breaking of the resonant chains by Andrei Sidoro, collaborators. They make the planets actually, they try to model the disk realistically. They get the planets to grow and to collide with each other and also to migrate. And they start populating a range of resonances, which are the market here. And this is the Peter ratio distribution that they get. If they remove the disk, of course, you get rid of all of these high order resonances because they're too closely packed together. And you start reproducing the Peter ratio distribution better. But this a bit of a bimodal thing. It's either if you populate these high order resonances, become unstable as soon as you remove the disk, because you don't have the eccentricity damping, or they become stable like forever in the resonant chain of like say 3 to 2 or 2 to 1. But there's been some recent work by Fei Dai and collaborators looking at the sample of systems that are in resonances as a function of 8. And this is mostly due to new observations from say TESS that is looking into younger systems and open clusters. And it's been found, even though the sample is small, there are about like 7 planets here. Most of the planets are in this bin. You could see the vertical error bars are very small. We know that the majority at the late stage is not in resonance, so it's fine. But it seems to be like most of the systems at an early age are in resonance actually, or close to resonance. Observability. If that's true, and it needs to be further tested. We need more observations to test this idea. It means that for the Kepler planets, the resonances are being broken in about 100 million years, which is an odd time scale. It's 10 to the 9 to 10 to the 10 orbits. It's long enough compared to the dispersal of the disk. People have thought about like mass loss from photoevaporation, but it seems to be very fine-tuned. And the overpacking there in the disk phase seems to be just like model. You just break the resonance as soon as you remove the disk, or they remain stable. So if they're perturbed externally, similar to the flyby, we may actually rely on Neptunes. And the reason is that there are not many cold Jupiters to produce an order unity effect on super Earth, because they're not that common compared to Neptune. So this mostly comes from microlensing, and this is the frequency of planets. It follows a power law. This is the log of the mass ratio. This band is roughly what I would define here as a Neptune. This band over here is a Jupiter. And the only thing that I wanted to say from this is that there are many more Neptunes than there are Jupiters. And they may be able to cause actually an order unity effect. So our proposal is planetesimal scattering breaking the chains of Neptunes. So we have a transiting chain of planets, the ones that are observed. We invoke planets called Neptunes outside with debris from the formation stage. And the motivation here, trying to sort of like match this 100 million year timescale, comes from the fact that we know that Neptune migrated outwards. It was possibly in timescales of the order of tens of millions of years. So getting close to this timescale, and this is planetesimal driven. That's the reason why it captures Pluto at 3-2 resonance. All Neptunes are common. There are many free-floating Neptunes, so you need a way of actually getting rid of the Neptunes. And this is a parameter space that actually has been properly studied. People have either focused on cold Jupiters and having ejections, or super Earth having collisions, but somewhere in between, where the Safronov parameter is close to unity in this box, is something that people haven't really studied properly. Okay, so these are, I'm gonna tell you in the last, I have 15 minutes. Yeah. The results from this, this is from a series of papers that are being led by Ryan LaRusso, who's actually an undergrad student here at Princeton. So this is at this point becoming like 3 papers, and so that's why it's a series. And I don't put a date because I don't trust myself. So the first stage, you just put the planets in resonances. You say that it happens the same as the Kepler planets. These are the Neptune. The fiducial set of resonance will be the 3-2. This is the most common for sub-Neptune planets. In the second stage, we just remove the disk and we leave the planets to interact with a planetesimal disk. And this actually is well motivated because the disks are actually common. In about 50% of the systems, FGK stars with ages below 100 million years. And this is actually the case over time. So you start losing some of these planetesimals to disruptions. And there is one example, OMIC, which is in the sample by Fei-Dai. We have like this decaying timescale for the number of systems in resonance. This is the 3-2, 3-2. And it has a very sort of these planets are transiting. So this is a net on the grid. There's been some work on this in the context of exoplanets. And in particular, when you just place 2 planets in a planetesimal disk, they seem to, by conservation of energy and angular momentum, they tend to repel each other. So they drift a little. And the amount of this drift is about the mass in planetesimals relative to the mass of the planets. We have confirmed this for 3 planets. And the question we're trying to tackle here is what happens in resonant chains that are more complicated. The outcomes will be a mix of collisions and ejections because the Safronov parameter is sort of the unity. So let me show you the results of the simulations. So I'm going to show you a sequence of snapshots. We have the planets here in the thick lines. These are 5 Neptunes at the 3-2. There is a planetesimal disk. We're actually varying the number of planetesimals, but this is a relatively simple one. This is after 1,000 years. After 10 to the 5 years, and by the way, the mass in planetesimal is about 1% of the mass in planets. So it's about like an Earth mass, which is a relatively small number, thinking that the migration of Neptune needed way more than that.
What is the size distribution of the planetesimals?
So these are all same size. We're actually working on that. This is a case where all the planetesimals are actually it's a full embody as opposed to working, for instance, with a planetesimals not interacting between themselves, like quasi-particles. So we're trying to now get a size distribution based on this other simulation, but at least we wanted to have something right, where all the we have control on the number of planetesimals and the gravitational forces. So the resonance actually breaks after about 100 vibration timescales very easily. You start ejecting some of these, and you had a scattering phase of these planetesimals in about 10 to the 7 to 10 to the 8 years. The angular momentum deficit, the amount of eccentricities and inclinations in the systems, it starts diffusively increasing until you get a first close encounter, and planets are actually lost to collisions, ejections, and tidal disruptions. This is 100 million years. This is a billion year, where we're just left with 2 Neptunes. We can repeat that for hundreds of simulations and see what are the different outcomes that we get. Again, because the Safran number is ordered unity, we get a mixed number of collisions to the number of systems that are tidally disrupted or actually ejected. But what is actually remarkably high, and I wasn't really expecting this, is that in about like there are 0.7 tidal disruptions per system. So almost every system leads to a Neptune being tidally disrupted or tidally captured.
By the central star?
To the central star, yes. And this is significantly higher than the cases of called Jupiters that people have worked on in the past. When Nadia, you asked about the numbers,
Yeah,
it's
this is-
10%. Yeah.
Yeah, this is exactly, going towards my question. So this is 0.7% of what? There's 0.70% of what? What is the range of initial setups for that number?
Right. So that's planets that start between 3 and 10 AU.
Okay.
They're in this chain. Of course, it's
So
modeled.
this applies to the planets that are formed in chains. That does not include planets that avoided the chains, right?
Yeah.
So this is specifically for those tidally.
Yeah, I'm not.
residence
So in these simulations,
planets.
we're not really still including the inner transiting chain. It's just the conductors. I'm going to show a simulation where we have the transiting chain, but this is just the conductors. So out of like 5 Neptunes, 0.7, actually, one of those either gets tidally captured, there are no tides in the model, or gets tidally disrupted. We can also quantify with different surface densities of planetesimals. Whether it's 1% in the mass of planets, or 2% or 4%, trying to estimate the time of the first encounter between the planets. It should be time here in log. So about like this would be 10 million years. So in order to get an instability time that is comparable to these 100 million year timescales, you need about like a 1 to 2% in planetesimals to get the system to destabilize in those times. And there is some dependence on the size distribution. So if you have more planetesimals, we're comparing here 50, 30 to 60, it actually gets longer the time scale, meaning sort of a grainy, more impulsive migration with a higher mass, less planetesimals, creates an instability faster. It's more destabilizing. And this is an example of a planet that it would be very close to actually being tidally disrupted. So here it's showing time, 7-meter axis, pericenter, apocenter distances. And you see that this is actually shooting very close to the host star. And in fact, the behavior looks very similar to episodes of secular chaos for the inner orbit because this is the semi-major axis, it remains roughly constant. It's like the outer Neptunes are doing their dance, changing energy. But the Neptune, the innermost Neptune, is being secularly excited. This is actually driving the high rate of tidal disruption, secular chaos. And this is actually mass dependent because the diffusion for the planets outside, how long they can actually stick around, it actually depends with the mass to the -2. It's the diffusion timescale, but the secular is just linear with the mass. So compared to Jupiter's, these Neptunes have longer timescale to stick around and secularly excite eccentricities of the Neptunes. If you see here the PDF, this is the minimum pericenter distance that any planet achieves. It's about like 80% of the systems approach as close as 0.1 astronomical units. 70% here is 0.7. There's a huge fish.
So, I mean, the reason I'm asking is that there is observational phenomenology that may or may not be associated with the tidal disruption and the diving of planets into the star, right? So there's infrared outbursts,
Yeah.
if you worry.
Yeah.
Then this sort of less luminous bit that may or may not be due to this. So you're saying 80%, but that's 80% of what, right? Like what, how restrictive is the set that results to these 80%? Like, is it 80% in the sea of like millions of
Yeah.
other systems that don't do this?
So in an optimistic scenario, it's 80% of sun-like stars that have Neptunes in these chains.
Okay,
Um,
okay, so then my earlier question was also how natural is it to form these chains to begin with? Like if you populate
Yeah,
a
yeah.
random system.
it's actually fairly easy to form it for the
Fairly,
Neptunes. Yeah.
fairly easy,
Yeah.
okay.
Yeah.
Okay, so it's a sizable part, so when we think about the mass versus separation, it's a sizable part of this, of the
No, part of the
space
space.
where this would apply.
I think so, but.
Yeah.
Yeah, I mean, the numbers that we have mostly come from microlensing, so as the velocities start finding
Right.
these Neptunes, which they will, then we have better statistics on that. So these are the different branching ratios as a function of planet mass. And this is the point that I was trying to make. So if you just pay attention, purpose of time, between tidal disruption and ejections, these are the systems that become unstable. So if the planet masses are very small, it's mostly planet-planet collisions because it's a Safronov number very small. So you mostly get collisions. And this drop as you expect. But something that I didn't know is that you can actually have now a difference as a function of planet mass between tidal disruptions and ejections. So if you go to Jupiter's, you get many more ejections per tidal disruption. So there seems to be a peak somewhere in the few Neptune mass where the planets linger around for longer and can secularly excite eccentricities and lead to even an enhanced rate of tidal disruptions. So that has a couple of.
What major axis do the systems need to reside in?
So it's not going to be that dependent on the semi-major axis. The eccentricities go to 0.99 very easily, but they started at 3 AU. So they need to get eccentricity to 0.99 to be tidally disrupted. So they could start even further out and you still get this.
Will they actually get tidally disrupted because the internal density of these planets is comparable to the internal density of the star?
Yeah.
So
It
it's swallowed.
We call it tidal disruptions, but it could be also tidal capture.
See, the capture is just a collision.
Oh, yeah.
But it's
Yeah,
not.
yeah, it depends on the envelope, but yes. Right, so because this is actually so prevalent. 5 more minutes. We're experimenting now with the cold Neptunes and resonant chains like TI level 6. But of course, this is extremely expensive. We're now evolving the orbits of very short period planets. But this is just to illustrate that in principle, the cold Neptunes could destabilize the inner chain. These are the ones that are observable, the short period planets. This is very expensive. We're trying to think about ways of tackling this. So stay tuned on this.
So this destabilization is happening due to some kind of resonance overlap or chaos is causing this? Like how is this destabilized?
So this is mostly long distance weak interactions. So you see here, we're indicating the first approach. So this Neptune here is approaching the chain, and you get some angular momentum deficit being excited there. There is a second encounter. It's a gradual process of diffusion. So you're transferring angular momentum deficit. And then there is just a very close encounter. You just break it off. It's more violent than that. It's not a... Okay, so Caleb, you have...
So you showed that a planetesimal disk can destabilize a resonant chain of cold Neptunes. If there was a planetesimal disk in the inner system, could that destabilize a
Absolutely.
chain of
Yeah.
Earth?
Yeah, in principle, it's scale independent.
Okay.
Modulo, the planetesimals are supposed to be ejected. If you do it for the inner chain, they collide with the planets, but you can still break the chains.
Okay.
The thing is that we're invoking about like 1% mass in planetesimals. It's like a 1 Earth mass. Whether you can actually have that amount of material in this region is something that are more suspect. It's easier to invoke this for cold Neptunes because we see debris is kind of is not too high a surface density of planetesimals.
Right.
But in these regions, like having a few Earth masses, it's a little bit pushing it.
Could the outer planets scatter in planetesimals to the inner system?
Exactly. There was a recent paper by colleagues at CIRA invoking that. Yes. Yeah, it doesn't have to be the Neptunes. Okay, so I guess I will finish with this. So if resonances are prevalent, the question of how are these disrupted? So our proposal is that planetesimal disks can actually disrupt the resonant chains of Neptunes, that in turn disrupt the inner chains. And the last couple of minutes, we'll describe some of the predictions from this model. Focus on one of those. If the planets are indeed being close to being tidally disrupted, it is possible that instead of tidally disrupted, they get tidally captured by the host star, something that is called as high-eccentricity migration. So we're tracking here what is the range of inclinations that you get as a function of the first approach within few different distances, but just focus on 3% of an astronomical unit. It would be something similar to the distance that you need for a tidal capture. Inclinations for these planets, if they get tidally captured, would be a broad distribution, but it has a median of about 80 degrees. And that's actually something that Juan Ignacio, who is here in the audience, has been working on Neptunes that seem to be in these polar orbits. So this is using the Rossiter-McLaughlin effect. If you look at the Neptunes, the sample of Neptunes, this is a function of stellar effective temperature and the projected stellar obliquity. The distribution seems to be peaking around 90 degrees for these planets. And many of these planets actually don't have cold Jupiter companions. So if something actually delivered them into these orbits that migrated, it actually could have been just Neptune themselves. Let's get this. The other prediction is planets that are free-floating planets. You get about 70% of the planets actually being ejected, but more than that, you get a significant population of detached planets. Planets that microlensing campaigns can actually are wide orbit enough that the microlensing event may actually be missing the primary signal. So they would be targeted as a free floating event. And those are actually comparable. About 70% of the systems remain on these very wide orbits. And that number seems to be more or less consistent with the ones that are with a big error bar found in free floating versus the bound system microlensing campaigns. So Neptunes may start in resonant chains. They may migrate through high eccentricity migration. Some of them actually are free floating. And Roman will have a big say on this as more planets are actually found in this region. About 1,000 planets are expected to be found in this box over here, and with about 100 systems of free floating planets. So maybe using the branching radius between these two populations can give a sense of how prevalent a model like the one that we're studying holds. So to finish, I talked in the first part about assembly due to resonances. I think planets actually do start in resonant chains. There is an intermediate phase of planet disk, planetesimal disk, that seems to break the resonances. This is the phase of the debris disk. And then in the late stages, different populations may emerge, including a dynamically hot population of multi-planet systems where you broke the resonances, free-floating planets, and hot Neptunes in polar orbits. So with that, I'll stop here. Take any questions. Thank you.
Any further questions for Cristobal?
What about planet-planet collision outcomes for, so you briefly mentioned them. At what distances from the star do they happen, roughly speaking? What's the,
So,
Yes. Right, so they happen about in 3-5 AU.
and it's not that few either. It's not probably-
Right.
Any more?
So in the post main sequence stage, you have wide dwarfs which you now need a mechanism of polluting. And previously, people have looked at the effect. I think it was Brad Hansen actually looked at the effect of using cold Neptunes roughly in the same orbits as you're considering to scatter, let's say, asteroids into the planet disruption radius of the white dwarf. And I don't recall them getting 80% of the asteroids ending up in being tidally destroyed. I mean, they were talking about maybe 10% or so, but definitely.
But these are Neptunes becoming unstable, or
probably not. No, it's probably, well, I mean, it's kind of a natural scenario for white dwarfs, right? Because if you have a system of Neptunes, they will become unstable probably because the mass ratios change as the central star is losing mass and so on. So here you're saying the key is the instability in the system of this.
is the nature of the instability, which is different from, say, cold Jupiters. In cold Jupiters, they just have a few close encounters and they're ejected, so they don't have enough time for secular chaos or secular torquing to be effective. So this would be, if you were to avoid planetary collisions, it becomes way more efficient if you start decreasing the masses of the planets. And it turns out that there is a peak for Neptunes because they avoid some of the collisions. So they get these long-term energy exchanges in the outer regions. And this was also studied by Samhara and Jianxin Wu for the free-floating population. Like they just stick around for longer. But the inner planet is actually getting all this secular excitation from these planets that stick around for long enough.
And this, what is the time scale on which this deep towards,
It's secular. So you see that the energy is conserved.
For several million years.
So it's gonna be several million years, yes.
And do these simulations include
GR, yes.
other precession effects, GR,
Yes.
spin of the star?
No, not the spin of the star. But GR they do. And
So GR is not stopping this.
no. No, you can do the back of the envelope calculation that, yeah, it's not supposed to, it's borderline, but it turns out that it doesn't inhibit this. And we have also a statistic of the planetesimals, so or the unity of the planetesimals actually, a significant fraction actually falls close enough to the star that could be tidally disrupted to.
Okay, I suggest we carry on the conversation for lunch and thank Cristobal.